Alright, so today's lesson is 6.2 part 2, video 2. These are now, so we went over some basic rules of counting, alright, where we, have our union rule, intersection rule, complement rule, and then just practice using in some basic settings where we'll actually do a lot of listing them out, because in these basic ones, sometimes it's easier to visualize by having them listed. Alright, so these are going to be basic examples of counting. These are experiments you're going to see over and over and over again. We're going to be continuing to use them throughout the semester, and we're going to use, so today's experiments are going to be flipping coins, rolling dice, and drawing from a standard deck. All right, and those are, again, like I said, we consider those basic experiments that we will run counting techniques on, probability, and eventually statistics with. So familiarize yourself with these type of experiments. All right, so the first one. For each of the following sets, we want to find the universal set and the count. We want to know how many outcomes are there. All right, I'm going to both list them and then count them. All right, so the first one's the easiest, simplest case. All right, the experiment is if I toss a fair coin. A fair coin just means that it's weighted fairly and I've got heads and tails on both sides. All right, so I toss a coin exactly one time. All right, well, I'm going to list the outcomes. There's only two possible outcomes, either to land on heads or to land on tails, right? That's it. There's only possibilities, heads or tails. All right, so the cardinality is there are two total outcomes, right? That's it. Two things can happen when you flip a coin. You either get heads or you get tails. And so that's the count. That's what we're doing here in chapter 6. We're counting. In the next chapter, what we're going to do is we're going to use, well, what's the likelihood, if I do this experiment, I'll get a certain event to happen. All right, so for example, heads. What's the likelihood heads will occur when I flip a fair coin? Well, there is one chance to get heads out of two total outcomes. So a 1 in 2 chance, or we like to say 50% chance. So that's where eventually we're going. We're not doing probability in this section. It's the next section, but we are counting. All right, second experiment. Same coin, so it's a fair coin, but this time it does change it. I'm going to toss it twice. All right, so 2 times I'm going to toss it. So what this is there are two groups. There's the first toss, all the possibilities, paired with the second toss and all of its possibilities. All right, so I'm looking at 2 tosses for my total outcome. All right, so I have my first toss paired with my second toss. All right, so remember, this is what happens on the first toss paired with what happens on the second toss. Well, this is the product property, that one we talked about before when we pair things together. So to figure out how many, it'd be the number of things that can happen in the first toss times the number of things that can happen on the second toss. Well, it's the same coin, so there's only 2 things that can happen on the first toss and only 2 things that can happen on the second toss. So it's 2 times 2 are 4 total outcomes. So there are 4 outcomes in my universal set. Now I'm going to list them because it's helpful to see the visualize to list them. And so I know I'm going to have 4. And I'm going to pair them together. I'm going to draw them as points and then I'm going to draw them without points. And so remember, when we did this before, we had pairs. The first part of my pair comes from my first outcome, so that's toss 1. The second part of my pair comes from my second toss. And so I can have heads on the first paired with heads on the second, or heads on the first paired with tails on the second. Tails on the first paired with heads on the second. Heads on the first paired with heads on the second. That would be the proper way to write it out. Now, due to time and just we shorthand things in mathematics, often we'll do this. Heads, heads is one outcome. Heads, tails. Tails, heads, heads, heads. And I will do this a lot with our tossing our coin. It means the same thing. It's the order that matters. So heads on the first toss paired with heads on the second toss. Heads on the first toss paired with tails on the second toss, which is different than tails on the first toss and heads on the second time because a different order. It was a different toss that got me heads and tails. And so eventually what we're going to do with this is we're going to look for probabilities. So right now we're just counting. There are 4 outcomes. But eventually what we're going to do is we're going to figure out, well, out of my 4 outcomes, what's the chance I get exactly, and I did heads, heads twice. Why I did heads, heads twice? Sorry, this should have been tails, tails. All right, tails in the first toss, tails on the second toss. So make sure you change that. That was supposed to be tails, tails. Those are my 4 different outcomes. If I had heads twice, they'd be 2 of the same outcomes. All right, so make sure you change that. That should be tails, tails. All right, so what was the likelihood that I get heads on both tosses? Well, there's a 1 in 4 chance, or 25% chance, of both tosses come out heads. Or what's the chance I get exactly 1 tail? Well, I get tails on the first toss, or tails on the second toss. So there's 2 chances out of 4, or 50% chance. All right, the next one is we're going to go up to 3, and 3 is about as big as I'll ever go. 3 tosses, although it would be extended to 4 or 5 tosses would work the same way. This one, I will set this up at a tree. So remember I said tree diagrams are going to be, we're going to hit the basics here. This is sort of the first easy example to introduce tree, to sort of list all my outcomes. Before I list it, though, I can figure out my count. So same fair coin, but now I've got 3 tosses. So I've got my first toss paired with my second toss, paired with a third toss. There are 2 outcomes on the first toss to be paired with 2 outcomes on the second toss to be paired with 2 outcomes on the third toss. So it's the Cartesian product rule, right? You multiply all the things you're going to pair together. And so it'd be 2 times 2 times 2, which would be 2 cubed, which is there are 8 total outcomes. So 8 possibilities when I toss a fair coin 3 times. 8 total different outcomes. All right, now I'm going to list them. So I know 8 should come out, but I'm going to list them. And like I said, I'm going to use a tree to set this up. And if you've seen a tree before, this should look familiar to you. If you're not, this again, we'll do more trees more in Chapter 7 than Chapter 6, but we're going to introduce them here. All right, so what we do is we have a set of branches. We have my first toss and its outcome. First toss. And then we set branches. That's what a tree has branches. And so the first toss has 2 branches. There's 2 outcomes. So first branch, possible outcome, second branch. Actually, I'm going to put them down a little lower. All right, so I can get heads on my first toss or tails. All right, then now I have the second toss. All right, and it has 2 outcomes, but my outcomes depend on what happens first. So either I got heads first, and then I'm going to have a set of branches where I can get heads and tails on my second branch, or tails could come out first, and then that branch has heads or tails. This would have been the last outcome. If you look at C, this would be the heads, 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 tails, tails, heads, tails, tails. All right, but now I'm going to do my third toss. And each one of those branches, each one of those end results on the second toss now has 2 set of branches to pair with them. So each one of those has the 2 possible outcomes on my third toss. So heads, tails, heads, tails, heads, tails, heads, tails. And I'm getting a little sloppy on my heads, tails. All right, and then I'm going to list them. And again, technically we would write them as a point, heads, comma, heads, comma, heads. But I'm just going to do them in the short format. So the first possible outcome comes from the end branches here. I can get heads on all 3. All right, heads on the first, second, and third. The next set is heads and then tails, and then so on. Heads, tails, heads. I'm going to try to be careful, make sure I do them right. Heads, tails, tails. Tails, heads, heads. Right, I'm reading down the branches is what I'm doing. So I'm kind of going down the path. Next one, tails, heads, tails. Tails, tails, heads. And tails on all 3 tosses. All right, and if you count them, there should be 8, right? Those are the 8 possibilities. And there are, if you count them, there are 8. And so there's 8 total outcomes when I toss a fair coin 3 times. And eventually what we're going to do with this is we'll count subsets and figure out likelihood. What's the likelihood all of my tosses come out the same? Well, all my tosses can either come out heads, or all my tosses can come out tails, and there are 2 of those outcomes out of 8. So it'd be a 2 out of 8 chance. All right, or what's the chance I get exactly 1 tail in my 3 tosses? That would be 1 tail and 2 heads. Well, I can figure out how many ways are there 1 tail and 2 heads. There are 2. There's just 2 ways to get, so 2 out of 8 tosses is to get 1 tail and 2 heads. Oh no, sorry, 3. Missed this one. 3. 3 out of 8. So again, that's eventually what we're doing. That's where we're going to do in the next chapter. Again, right now we're just practicing the sets. But this is a set you're going to be familiar with. We'll do a lot with tossing a coin 3 times. All right, so make sure you're familiar with the set. All right, the next one we'll also be doing a lot with. There's always There's going to be 1 or 2 questions on the first quiz that will have to do with rolling a pair of distinguishable dice. Basically, there'll probably be one on all of the 3 exams that are coming up, or 3 quizzes that are coming up. There's always one on the final, or 2 or 3, or a handful. All right, so this is another set you want to make sure you become very familiar with. You'll be seeing it again and again and again. All right, so we're always going to be in this class. There is a difference between, and your book talks about it a little bit, between distinguishable and indistinguishable dice. We will always do distinguishable dice, meaning you can always tell the difference between our dice. They're either 2 different colors, like my example here. I've got a red dice and a white, so you can tell which one popped up what color. Or we'll roll them like we did with the coins. We'll roll the first toss and then the second toss. And so we can distinguish between tosses, just like the coin example. Alright, so first I'm going to find these with a table, but before I do that, I'm actually going to figure out how many there are before. Alright, so I've got my outcomes on the red paired with the outcomes on the white. Right, this is the Cartesian product. So it's the number of things that can happen on the red dice times the number of things that can happen on the white dice. Well, the red has 6 possibilities, right? The red dice, when I roll it, can show 1, 2, 3, 4, 5, or 6. The white also has 6 outcomes, so it'd be 6 times 6 for a total of 36 outcomes. All right, there are 36 different outcomes when I roll 2 distinguishable dice. All right, and that's always going to be our case, 2 distinguishable dice. So these 36 outcomes, you're going to want to make sure you know how to find and understand. All right, so I'm going to use a table to help me out. All right, so I'm going to draw my table here, where on the top row is going to be the red dice, and the bottom, or the side here is going to be the white. So the red dice can have the numbers 2 through 6, or not 2 through 6, 1 through 6. And the white dice can also have the numbers 1 through 6. And I will write these as pairs because it's a little easier to see. Now you could shorthand it if you want to 1, 1, like I did with the heads, tails. But this one I'm actually going to write it as the pair like we usually do. So one outcome is I get 1 on the red dice and 1 on the white dice. Or I can get 1 on the red, 2 on the white, 1 on the red, 3, and then so on. The 1 with the red is paired with each of the numbers on the white. So 1 all the way down to 6. And then 2 on the red, paired with all of the numbers on the white. And then 3, and so on. Alright, so again, this is something you will know how, you'll have to know how to do this when we ask you a rolling dice example. More often than not, we won't provide you with the set. You will have to come up with it. But it's not too hard once you've done it a couple times. I mean, the pattern kind of emerges. The biggest thing is just make sure you're careful. Like that. 5, 5, and then 5, 6. And then there are your I'm getting a little messy here. There. Alright, I should double check and make sure I didn't do anything wrong, but there should be 36 different outcomes. So it should be paired with 1 paired with 1, 2, 3, 4, 5, 6, 2 paired with 1, 2, 3, 4, 5, 6, 3 paired with 1, 2, 3, 4, 5, 6, and 4, same thing. 5 paired with 1, 2, 3, 4, 5, 6, and 6 paired with 1, 2, 3. I got a little tired here, I think, at the end. 3, 4, 5, 6. There we go. Now they're in the right order. And there's my 36 outcomes. Alright, so that's where sometimes it's helpful to use a table. Though you don't have to. Some students can just draw that out verbatim. Alright, now we're going to do, so there's the universal set. Alright, there's all 36 possible outcomes when I roll 2 distinguishable dice. Now we're going to look at subsets of that, which we're going to just count them. Again, eventually we'll do probabilities. Before we do probabilities, we have to know how to count, because we can't do probabilities until we know how to count. Alright, so consider the experiment of rolling a pair of distinguishable dice. That's what I drew up here. I went ahead and put a nicer one in because I know my handwriting tends to be messy on my tablet. And so I wanted to make sure I had a nice clean set to work with. Alright, it's the same set I had above. Numbers are in slightly different order, but it's the same 36. Alright. I just flipped where my 1 and my 2 went. But they're all the same. Alright, all 36. So the number total here in my universal is 36. If you count them, there are 36 possible outcomes if I roll 2 distinguishable dice. Either they're 2 different colors, or I did the first roll and the second roll. Alright, so the 1-1 represents the first number is the first roll, the second number is the second roll, or the first number is the red dice, the second number is the white dice. Alright, now we're going to look at these subsets. So all of these should be groups of my 36, but less than my 36. So these are going to be proper subsets. Alright, so the first one, and I'm going to use highlighters and colored pencils. This might be a good idea if you're doing this on your own and you're following along and you're drawing them all out, to have maybe highlighters with you or colored pencils when you write out the sets so you can color the subsets. It just makes it a little easier when you color the subsets. Alright, which is what I'm going to do. Or circle them. Alright, I'll probably use both circling and highlighting. Alright, so E, subset E, is going to be the sum of the dice is 6. So I'm looking for the number of ways to get E. So how many out of my 36 have a sum of the dice is 6? And what's nice about this is sums go by diagonal. A sum meaning I add up my two numbers. So a 1-1 would add up to 2. A 2-1 is 3, and those are both of those. A 3, 4, and then there's my 6. So I'm going to do a highlighter. And so 5-1 to 4-2 to 3-3 to 5-1. And so there's my set E. All right, blue color represents my set E. All right, and then I count them. All right, there are 5. All right, 5 ways. So if I were looking for probability, there'd be 5 possible ways out of 36 to get a sum of 6 if I roll 2 distinguishable dice. Alright, the next one is F. F is the set of outcome where at least one die shows an even number. And we're going to be using that term at least and at most. So at least one die shows an even number, meaning I can have a result with one even number or more. Or more would just mean both dice shows an even number. Alright, so F is a fairly large set. It's actually easier. I am going to find F. But it's actually easier to find the complement of F. So I'm going to write out what the complement of F is. F, not F. Alright, not F would be the opposite of getting a sum, or the opposite of getting at least one even number. Well, the opposite of getting at least one even number is no even numbers. So that means both numbers are odd. Which is actually the smaller set. So I'm going to figure out the number of outcomes not in F, and then use my complement rule to figure out the number of outcomes in F. Alright, I'm going to use my yellow highlighter to do the number of outcomes not in F. Alright, again, both should show up as odd. And so basically, as long as it doesn't have an even number in it, it's this case. So 1-1, 3-3, 1-5, 3-1, 3-3, and so on. Alright, and so if I count right, there should be 9 outcomes. Oops. Where both are odd, which is the complement to the set I'm looking for. So that means I want to throw those 9 out and keep the rest of them. So everything that's not highlighted in yellow, which would be taking 9 and subtracting it away from 36. So if you take 36, subtract away the 9 that have both of them odd, that'll leave me with the ones that have at least one even number, and that means there are 27 with at least one. If you look, the ones that aren't highlighted will have at least one. Some of them have 2 even numbers, but they have at least one even number in them. All right, so there are 27. So if I'm looking for rolling a pair of dice, and I want to at least get one even number, well, I've got 27 chances out of 36. I only have 9 chances not to get that, or 9 chances out of 36 to get both odds. I believe there's G. So G is we're looking for the subset of outcomes where at least one, so there's that phrase at least one, shows a number 5 or greater. So that means at least one, meaning one dice or both dice, shows a 5 or greater. Well, the only number greater than a 5 when I roll a dice is a 6, right? And so I want all of the outcomes where I get at least 1, 5, or 6. So meaning I can show up with a 5 or a 6. Alright, so the number in G, which I'm getting at least 1, 5. And so basically it's the last 2 rows in column. So both of these have a 5 or 6 in them, so all of these, and then up here. Alright, so if you look at that set that I've circled there in my black, those are all of the ones, if you look at them, those are all of the ones they have a 5 or 6 in the pair. Some of them have both, right? These down here have both a 5 and a 6 in the pair, these 4. The ones that aren't in my black group there, where I've circled them in my black pencil, don't, right? They don't have it. And so I just count those, and I believe it should count up to 20 if you count them. All right, so there are 20. If I'm rolling dice, there's 20 possibilities of rolling a 5 or a 6. At least a 5 or a 6. All right, so 20 total. All right, now I believe we're going to combine with our and or statement. So we're counting, and then we're combining with union and intersection. I'm actually going to write out in words what it means, and then we're going to go look at it and see what it is. So this is why it's very helpful to have the set all drawn out for you. Also, it's helpful to kind of do colors so you can kind of see where things are. Alright, so E, and remember this is the and symbol. So I want everything in. So I want the number in E and at the same time in F. So remember, E was I want the number with a sum of 6, and F has at least one even number, right? That's what F was. So I want to go figure out how many have both of those things true, right? And means both of them have to be true. So they have to be in E and F. And E is the one I'll start with because it's the smaller set, right? E is the one I've highlighted here in blue. There were 5 outcomes. F, remember, is at least one even number. And so if I look at the blue set, there's only 2 outcomes in the blue set in E where I have even numbers, right? The 4, 2 and the 2, 4, it. The rest of them are the odd cases, the not in F cases. And so there's only 2. The answer is 2. There are 2 possibilities where I get in the group E and F at the same time, where I have a sum of 6 and at least one even number. All right, so the answer to that one is 2. All right, this one's the or statement. I always have to be careful with the or statement. So I'm going to write out in words, and then I'm actually going to use my formula, so I'm careful not to count anybody twice. We don't ever want to count people or items twice. All right, but first I'm going to explain what it means. So not F, which we actually have highlighted. All right, so not F or in G, right? I want not in F or, right, that's the or symbol. They can be in G. All right, so in words, not in F meaning both of them are odd, right? No even numbers. So both numbers are odd, or they have at least one number 6 or 5. All right, so I want all of the outcomes where both are odd, or, and remember, or is all inclusive. I can be in one set or the other. And the biggest thing with the or is you don't want to count people twice. So I'm going to use my or formula. All right, so remember the formula is number in my not F group plus the number in my G group minus anybody who might have been in both groups, right? Both not F and in G, right? Because I don't want to count anybody twice. So if I count people from the both odd, I count people from the getting a 6 or a 5. Well, there are some that are shared in both, and I want to make sure I don't count those guys up. Now, there's a couple ways you can do this. You can use the formula, or you could just flat out count them. I'm going to use the formula because I think it's just good practice to do that. All right, so if I go back and look at my picture, remember the number not in F were the ones highlighted in yellow. There are 9 possibilities of not being in F, which means both are odd, right? Those are the ones highlighted in yellow. If you count, there are 9 of them. All right, so there are 9 not in F. Remember, there were 20 in G. All right, so if you look at this was G. 20 in G. But remember, I counted some of them twice, right? The 5-1, the 5-3, the 5-5, the 3-5, and the 1-5 are in both. So I counted both of those in the 9 that went with non-F and the 20 that were in G. And so I've got to make sure to subtract 5. So I only count them once. All right, so I've got to subtract 5. All right, so then the final answer is 9 plus 20 minus 5, which is 24. All right, so the number, not in F or in G, is 24. All right, that's one way to do it using the formula. Again, it's always a good rule of thumb with the or to do the formula so you don't accidentally count somebody twice. The other way you could have done it is you could have counted everybody in G. All right, so that would be the 20 in G, knowing that you've already counted those 5, and then just add the 4 that land outside here that are highlighted in yellow. All right, so that would be the 20 in here plus those 4 in yellow. Like I said, there's more than one right way to get to the answer. Just make sure you're careful. All right, you want to count the right number. You don't want to count those 5 guys that are inside twice. So you don't want to take 20 plus 9. There aren't 29 different ones because 5 of them gets counted twice. All right, so just make sure whenever you're dealing with the or statement, nobody gets added twice. All right, the last one of this set using our set of 2 distinguishable dice. All right, so the last one is I've got this prime symbol on the other side of the group E or G. And so first it's not from the set E or G. All right, and so I want to be not from the not a sum of 6 or have at least 1, 6, or 5. All right, so those are what I don't want. I don't want a sum of 6 or have, so I don't want, basically this one I'm going to eliminate. I want to eliminate anything from set E and anything from set G, and everything else is what I'm looking for. I'm looking for everything that's not in E and everything that's not in G. And so basically I'm just going to cross a bunch of stuff out. All right, so I'm going to go back to my picture here. All right, I don't want anything in E, so anything in this blue I don't want. I don't want anything in G, so nothing in this set G. I don't want anything there. So I'm crossing out what I don't want, which means everything that's not colored out is the group I'm looking for. So it's these up here and this set of 3 inside, and then I just make sure I'm careful when I count them. All right, I count 13, so hopefully you count 13 as well. So there are 13 outcomes that do not land in G, which have a 5 and a 4, and are not in E, a sum of 6. All right, and if you look at them, all of the outcomes that are not crossed out do not have a 5 or 6 in it and are not a sum of 6. All right, so that answer was 13. There are 13 in that last group. All right, and that finishes up the rolling 2 dice. And again, make sure you're familiar with it. You'll see rolling dice again and again. There'll be a question about it. All right, the last example from this set of notes from this video is a standard deck of cards. So with video games and all of that out there, students tend to be not as familiar with a deck of cards as they were in the past, but it's just another one of those staple probability and statistic tests that experiments we tend to do. All right, so in case you're unfamiliar with a standard deck of cards, in this class our standard deck is always 52 cards. Standard means there's no jokers. And so what a deck of cards is there are 4 what we call suits with 13 cards in it. And so the suits are, the first one here is hearts. All right, and there are 13 of those, diamonds, clubs, and spades. All right, and there are 13 of each. If we count them, there are 13 hearts, 13 diamonds, 13 clubs, 13 spades. All right, these are our face cards. All right, those are the jacks, the queens, and the kings. This A is an ace. All right, and then everything else in between is the numbers 2 through 10. All right, and half of the deck is black. The spades and the clubs are the black cards, and the hearts and the diamonds are the red ones, and you can see that they're colored for you there. All right, so that's what our standard deck is. And so now we're just going to ask you questions on it. All right, so the first question is, let E be the set of face cards, let H be the set of hearts. All right, so we have our face cards, which are our J, Q, and kings, K. All right, so face cards are just the J's, the K's, and the Q's. All right, jacks, queens, and kings. All right, and our H is our set of hearts. And so what we're looking for, well, we want the number of, right, because that's the count, number of face cards, right? E stands for face cards. Or, right, that symbol means or, not a heart. All right, and what we have to be careful of with the or statement is nobody gets counted twice. So I'm going to write it out just because, again, I think it's good practice to write out the union rule. All right, so number of E plus the number H prime minus any that were in both E and not H. All right, so I don't want to count those guys twice. So E is first, the number of face cards. All right, so my face cards are my jacks, queens, kings. All right, so those are my face cards. All right, there are 3 face cards in each suit, and so there are 12 face cards. All right, so there's 12 of those. Not hearts. All right, so not hearts would be the clubs, spades, and diamonds, right? These would be the not hearts. So I throw away the hearts. The hearts would be, so out of my 52 cards, I throw away the 13 hearts, so there should be 39 that are not hearts. All right, if you count them, there should be 39 there that are not hearts. But that one's easier probably to do the complement. I throw away the 13 hearts, and I'm left with 39. If you can't read my 39 there, that are not. All right, so 39 cards are not hearts. Minus anybody that got counted twice. And there were cards that got counted twice. The cards that I counted twice were the cards that were both face cards and at the same time not hearts. Well, that's this group here that's in the overlap, right? The overlap is the and statement. These 9 cards, right, there are 9 of them there, are all face cards that are not hearts. And so I counted them twice. They were counted in the face card count, the 12 count for face cards, and they were counted in the not hearts count. All right, so I've got to make sure, well, I don't want to count them twice because there's only 1 card of each in a deck. And so I've got to make sure to subtract those 6 so they aren't counted as double. All right, so, or not 6, 9. Those 9, so they aren't counted as double. There's 9 of them, if I count, 9. All right, and so I take my 12, my 39, minus my 9. And so the number of face cards or non-hearts is 42. There are 42 possible cards. Now, there's an alternative to this. I wanted you to do good practice using the formula. An alternative to this is, if you look at it, I've circled everything here. Those are my non-hearts and then my face cards. If you look, there's these cards here are the only ones I don't want. All right? And so there's 10 of them if you count ace through 10. There's 10 cards. I could throw those 10 out. So I take my 52 cards, subtract away those 10, would leave me with 42. That's an alternative way you could have counted. All right, and again, like I said, there's more than one way to do this. As long as you get to the right answer, that's what's important. All right, the next example. How many ways can you draw a card that is both a black card and an ace? So number of cards that are black and an ace. All right, so and is always easier. There's both of those things. If I go up and look at my standard deck, well, I just look at the black cards, there are only 2 of them that are black aces. All right, so there's only 2 possibilities. So the odds of that is low, right? There's only 2 out of 52. I only have, if I have the whole deck and I'm drawing a card out, I only have 2 chances out of 52 to get a black ace. All right, the last one. A card that is less than 5 or an ace. So number of ways to get a card less than 5, or it's an ace. All right, so remember, it's less than 5. Less than 5 would be 4, 3, 2, right? Not including 5. It's less than 5. All right, so I go back up here. I want all of the cards that are less than 5. Well, that basically is cutting me off here. Or an ace. So if we were playing, blackjack, all right, and I need a card that is smaller than 5, where aces can count as 1. All right, I want to know what's the chance I draw a card if I have the whole deck What's the chance I pull out a card that is smaller than 5? Well, there are, if you count these up, 16 possible ways to do that. All right, 16 possible ways. So 16 out of 12, 16. There are 16 cards that are less than 5 or an ace. So 16 possible outcomes out of 52 would be the chance that that happens. All right. All right, so that finished up. So make sure you're familiarized with these. Like I said, flipping a coin, rolling a dice, and drawing from a standard deck. You're going to see these experiments over and over and over again over the next 8 weeks of the semester. So make sure you make yourself familiar with this set of notes. All right, we're going to be adding to these as the semester goes on. So these are sort of the basic notes. All right, so that finishes up this video. The next video is going to be on Venn diagrams and applications using Venn diagrams.